day of SAS23. So this session is about cost precision trade-offs and acceleration. And we are going to start with a talk on ADCL, acceleration-driven closed learning for constraint Horn clauses. So this is work by Florian Frohn and Jürgen Giesl from Aachen University. And Florian is going to give the talk. So Florian, the floor is yours.
So thank you for the introduction. So ADCL is a new calculus to analyze the satisfiability of constraint Horn clauses, or CHCs for short. More precisely, we're looking at linear CHCs. We'll explain what that means in a minute. If you're not familiar with CHCs, then for the sake of this talk, you can simply think of them as transition systems, and I will comment on that throughout the talk from time to time. And as you all can already see from the name of the calculus, acceleration is the core ingredient here, so I will explain what that means in a minute. But before that, let us have a look at one of those CHCs to see what they look like. So essentially, this is just first-order logic, where we are looking at restricted forms of formulas. So all these formulas are implications. We always have at most one uninterpreted predicate symbol on the left-hand side, one uninterpreted predicate symbol on the right-hand side. And in addition, we have some constraint with respect to some background theory. So in this case, that would be integer arithmetic. So in a nutshell, this formula tells you if f of xy holds and x is bounded by 5,000, then f of x plus 1 y holds as well. And if you prefer to think of that as a transition system, then, well, f is basically your location in your control flow graph, and then this transition here tells you if f is reachable with the valuation xy and x is bounded by 5,000, then f is also reachable with the valuation x plus 1 y. And if you go from CHCs to transition systems, then unsatisfiability becomes unsafety and satisfiability becomes safety. Okay, now the goal of acceleration techniques is to take a clause like this one here, which is conjunctive because we do not have disjunctions in this constraint here. So in general, the theory part here may also contain disjunctions. And it's recursive because we have the same predicate symbol on the left-hand side and the right-hand side. Of course, in general, that does not have to be the case. So we start with such a clause, and then our goal is to compute a new clause, which I called phi plus here. And essentially, the idea is that everything that can be derived from your original clause via resolution in arbitrarily many steps can be derived from your new clause in just a single step. Or in the setting of transition systems, everything that is reachable with your original transition in arbitrarily many steps is now reachable with your new learned transition in just a single step. So more formally, the ground instances of your CHC, which result from instantiating the variables with some substitution that satisfies our constraint. So the ground instances of the new clause are the union over everything that you can get from your original clause via resolution. So this notation here simply means that we resolve phi with itself n times. Okay, so that's the basic idea. What does that mean for our example? Well, we introduce a new variable, which is called n here. It needs to be positive. And now this new clause should simulate n steps with our original clause in just a single step. So instead of incrementing x by 1, we increment it by n. And then we need this additional condition here, which guarantees that the condition of our original clause is indeed satisfied throughout n steps of resolution. So that's how it works. And just to convince you that this is not something that I made up, there are quite a few approaches in the literature that present techniques how to compute such accelerated transitions or accelerated clauses. Okay, now why is it a good idea to use these acceleration techniques for satisfiability of constraint Horn clauses? To illustrate that, I would like to introduce my leading example. which consists of these three clauses. The first one is what we call a fact. It does not have an uninterpreted predicate symbol on the left-hand side, but just a constraint. So in the setting of transition systems, that would basically correspond to your initial states. So you start with something, so you start at location F, and X is bounded by 0, and Y is bounded by 5,000. Then our second clause is a recursive rule, which now has a disjunctive condition. So here you can see the disjunction here, and the clause that we've seen at the previous slide basically corresponds to this first case here, okay? And then the last clause is what we call a query. So the right-hand side does not contain any uninterpreted symbols, but it's simply bottom. And that corresponds to your error states in the setting of transition systems. So once you've derived f of 10,000, 10,000, you immediately get a contradiction, which means unsatisfiability, and in the context of transition systems, that would be unsafety. Okay, so how can we prove unsatisfiability of such a set of CHCs in a kind of traditional way? Well, we could do it like that. We start with our fact, where we instantiate the variables by suitable values, like x with 0 and y with 5,000. Then we obtain this state here. Now we can apply our second clause 5,000 times. More specifically, the first case or the first implicant of our clause. So an implicant is just a conjunctive variant of our potentially disjunctive clauses. Now this first implicant applies 5,000 times because it applies whenever x is bounded by 5,000. So if we start with 0 and increment it 5,000 times, then we end up in this state here. Then the second implicant of our clause applies 5,000 times, which increments x and y simultaneously, because y is now set to y prime, which is equal to y plus 1. So after 5,000 steps, we end up in this state, and then we can apply our last clause and get a contradiction. So what's wrong with this reasoning? Basically nothing, but it takes more than 10,000 steps. So if you use a technique that relies on some kind of iterative deepening, like bounded model checking, for example, it's going to work eventually, but it's going to take some time to unfold the relation like 10,000 times. So we propose a different kind of reasoning, where we first have a close look at implicant 2a, and I already mentioned that this is the same clause that we've seen on the previous condition, so we already know what happens when we accelerate it. We get this new clause here. Then we can have a close look at implicant 2b accelerated as well, and in this way we obtain clause number 5, where now x and y are incremented by n instead of just by 1. And then we get a much shorter proof, which looks like that. So again, we start with our fact and get f of 0, 5,000. Now we can simulate 5,000 steps with clause 2a in a single step and jump straight to f of 5,000, 5,000. Then we can use our second learned clause to simulate 5,000 steps with clause 2b and jump straight to f of 10,000, 10,000. And then we can apply our query after just 3 resolution steps, and we get a much shorter proof. Okay, so this reasoning was kind of ad hoc. Now we wanted to formalize that in a way that we can automate. And to this way, we came up with our calculus ADCL, which essentially consists of these 4 rules here, which may look a little bit shocking, but that's essentially the formalization of our whole technique. So if you see it from that angle, it's not that shocking anymore. So I'm going to give you the high-level intuition of those 4 rules first, and then we are going to see how they operate on our example, okay? So the states of our calculus are those pairs here, where the first component is what we call a trace. And a trace is simply a sequence of CHCs, which always starts with a fact, so an initial state, if you want to see it like that. And as an invariant of our calculus, the resolvent of our trace, so if you just resolve those clauses from left to right, always has a satisfiable condition. So in the setting of transition systems, this sequence corresponds to an actual program run. Okay? So our goal is to find such a trace that ends with a query, because it always starts with a fact. So if it ends with a query, then we have derived the contradiction, so we've proven unsatisfiability. The second component of our states is a vector of sets of blocking clauses. And here the idea is that the elements of the last set of this vector may not be used for the next resolution step. So in this way, we can block certain parts of the search space such that we do not visit them again. Okay, the CHCs that we are analyzing are in this set capital Pi here, and this abbreviation here means syntactic implicant projection, which is a bit technical. I'm not going to go into the details here, but essentially that tells us that we do not use the clauses as they are, but we use those implicants, those conjunctive variants of our clauses for resolution. And that's important because in this way we make sure that only conjunctive clauses end up on our trace. And in this way, we can use our acceleration techniques, which only work for conjunctive clauses. Okay? So what this first rule does is it simply picks one of our conjunctive variants of our clauses, it appends it to our trace, and it appends an empty set of blocking clauses here. So it just makes one step with a CHC. Okay, the second rule is for acceleration. So if our trace has a suffix which is recursive, then we plug this suffix into an acceleration technique. In this way, we derive a new clause. We replace our recursive suffix with our new learned clause, and we block this learned clause for the next step. So why do we block it? Because these learned clauses, these accelerated clauses, basically correspond to transitive closures. So using them twice in a row is kind of pointless. Everything that can be done with 2 occurrences of such a clause can also be done with just a single occurrence of them. And for that reason, we don't have to consider traces where the same accelerated clause occurs twice subsequently. Okay, our third rule is for the case that our trace has a suffix which is redundant for a certain notion of redundancy. I will explain a little bit more about that later on. And in this case, we can backtrack. And backtracking simply means that we drop the last element of our trace and block it. And there's a second case where we can backtrack, which is, well, when we are stuck. When all clauses are either blocked or appending them to our trace would result in a trace whose resolvent has an unsatisfiable condition. In this case, we can backtrack as well, because there's no way to make progress from such a state. Okay, so how does that work on our example? Here are our 3 clauses again, and the learned clauses are grayed out because we haven't learned them so far, right? And then we can start to construct our proof. And the initial proof state always looks like that. So the trace is empty, and we have an empty set of blocking clauses here, so nothing is blocked for the first step. Then we start with a fact, because as I mentioned, the first element of the trace always has to be a fact, with our rule step, and we append another empty set to our blocking clauses here. And on the right, I show you one possible model for the resolvent of our trace, just to give you some idea where we are in the state space. So there are many other models here. Those are not unique. They are just to give you some idea where we are. Okay, now we can apply our second CHC, but as I mentioned, we do not apply it as it is, but we use one of those conjunctive variants, in this case, implicant 2a. And what's important is that we compute these implicants lazily. So I just highlighted implicant 2a here because our implementation wouldn't care about implicant 2b at this point. And that's important because there can be exponentially many of these implicants in practice. Okay, now I'm going to do something stupid, which wouldn't be done by our implementation, but I want to illustrate something by doing that. So let's make another step with our clause 2a. Then we end up in a state like this here, where x is, for example, 2. Okay, but at that point, we should really apply our acceleration technique because our trace has a recursive suffix, namely clause 2a. And we've already seen what happens when we accelerate it. We obtain clause number 4 here, which increments x by n and can simulate arbitrarily many steps with clause 2a. So we replace the last element of our trace with our learned clause, and we block this learned clause for the next step. Okay, at this point, our trace has a suffix which is redundant. Why is that? Well, these clauses here together, 2a and 4, they simulate effectively at least 2 and possibly more steps with our clause 2a, right? Because 4, remember, corresponds to the transitive closure of 2a. So it can simulate one or more steps with clause 2a. So if you take these two clauses together, they can simulate 2 or more steps with clause 2a. That's strictly less general than just clause 4, which can simulate 1 or more steps with clause 2a. Hence, these two clauses together are redundant, because everything that can be done with them can also be done with clause number 4. Hence, we can now backtrack and block clause number 4 for the next step. Now we are again in a state where our trace has a redundant suffix, because 2a is strictly less general than clause 4. So we can backtrack once more and block clause 2a. And now we can do another step with our accelerated clause number 4 and end up in this state. So that's basically the reason why I did this somewhat stupid step here, where I should have used where I should have used acceleration straight away, and instead I used clause number 2a a second time. And this way we ended up in a state where we have a redundant suffix, so that I could illustrate how to use the rule covered. Okay, so at this point we are in a state like x 5,000 and y is 5,000, so we can use the second implicant of our clause number 2, which is implicant 2b. And it increments x and y by 1. And now we can use acceleration again, because clause 2b is recursive, and learn our second accelerated clause, clause number 5, which we've seen before as well. In this way, we can simulate arbitrarily many steps with clause 2b at once, and finally apply our query, clause number 3, to derive a contradiction. And now we've successfully proven unsatisfiability of our CHCs. Okay, now we haven't seen how to use the last rule of the calculus. So just to illustrate that, let's forget about clause 3. Let's pretend that it doesn't exist. Then the last step doesn't work anymore. And now we are in a situation where we are stuck, because clause number 5 is blocked explicitly, and clause number 2b is blocked implicitly here, because clause number 2b is redundant with respect to clause number 5. It's strictly less general. So if we block a clause with these blocking clauses, we implicitly also block everything that is redundant with respect to them. Okay? So we cannot use clause number 2b, and we can also not use 2a or 4, because they require that x is bounded by 5,000. But the last element of our trace is clause number 5, which requires that x is greater or equal than 5,000. So we cannot apply them either. Hence, we are stuck. And in this case, we can backtrack using our last rule. So we drop clause number 5 and block it. Now, we could continue with this example by doing more steps and backtracking and so on. Then eventually we would reach a state like that, where the trace is empty and our only fact, clause number 1, is blocked. And whenever we reach a state like that, where the trace is empty and all facts are blocked, then we have proven satisfiability. So then we have shown that our set of clauses is satisfiable. Okay, so that's how our calculus works. Let's look at some numbers, because we've implemented all of that in our tool LoAT, the loop acceleration tool, and compared it to a few other tools. So the implementation of bounded model checking in Z3, the implementation of the spacer algorithm, which is kind of the state-of-the-art algorithm for satisfiability of CHCs, and it's also implemented in Z3, and transition power abstraction, which is implemented in Golem, and Seeger loop, which is implemented in Eldarica. And as you can see, our implementation cannot prove satisfiability at the moment, because we use certain approximations that are unsound for satisfiability. So far we have focused on unsatisfiability. We'll talk a little bit more about that later on. But you can see that for unsatisfiability, we are quite competitive. So bounded model checking is a bit more powerful. Spacer and LoAT are almost equally powerful. And you can see that we can solve quite a few instances that cannot be solved by any other tools. And if we look at these instances a bit more closely, then you can see something quite interesting. So the counterexamples, the refutations that LoAT finds, are pretty short. So 15 steps at most. Now, of course, these refutations use our learned accelerated transitions that can simulate many, many steps at once. So you can map these resolution proofs back to proofs that only use original clauses that were already part of the input. And if you do that, then you get proofs of this length here on the right-hand side. So something like, I think, 684 million steps. Well, good luck with finding something like that with bounded model checking. So for these problems, you really need techniques like acceleration. And if we look at the runtime, well, you can see that bounded model checking, spacer, and our implementation, so ours is the black line, the yellow one is bounded model checking, and the blue one is spacer, are all essentially equally fast in practice. Okay, so to conclude, we've introduced a new calculus that can prove satisfiability and unsatisfiability of constrained Horn clauses, even though our implementation is currently restricted to unsatisfiability. It's refutationally complete, so if your set of CHCs is unsatisfiable, then you can prove it with this calculus. Unfortunately, it does not terminate in general, so even if you impose some reasonable restrictions on the strategy, how to use the rules of our calculus, you still cannot guarantee termination of the calculus, unfortunately. I've talked about this notion of redundancy quite a bit in this talk. Unfortunately, automating that is quite challenging. So that's one of the points where we have to use approximations. So we use a sufficient criterion for redundancy in our implementation, which is one of the reasons why we cannot prove SAT. And our acceleration techniques are, of course, incomplete. I mean, you cannot always compute these transitive closures precisely. So here we sometimes have to resort to approximations, and those approximations are also just sound for unsatisfiability. But on the bright side, it's orthogonal to the state of the art, so we can prove quite a few things that other tools cannot prove, and it finds significantly shorter refutations than other tools due to its use of acceleration techniques. So thank you very much for your attention.
Okay, thank you very much, Florian, for the talk. So are there any questions in the room or online? So please. Yeah.
Thanks for the very comprehensive talk. No. Should I speak up? It's not what I asked. Can you Yes.
Just use mine. Take the broken one.
Okay, thanks again for the comprehensible talk. I mean, for humans, it's quite clear that we want to instantiate n to 5,000 in your example, but how does your tool instantiate those variables?
So let's go back to this example. So in this example, I showed you these models on the right-hand side, right? The point is that in practice, these models are not part of your state. So the SMT solver that's running in the background just chooses any model, but it can change to a different model at any point. So let's consider this state here, where the last clause is clause number 4. You're perfectly right. Now the SMT solver might say, okay, let's set n to 1. That's perfectly okay. In the next step, well, we cannot use clause number 4 again because it's blocked. We cannot use clause number 2a again because it's blocked. So all we can do is we use clause 2b, and clause 2b requires that x is at least 5,000. So at this point, when we add the constraint of clause 2b to the SMT problem, the SMT solver has to switch to a different model where n is instantiated with 5,000. So essentially, the important bit here is that the model is not part of the state, so it can change at any point. And hence, if we make a bad decision with respect to this new variable n, it's not such a big deal.
And then it jumps back and forth and finds the n equals 5,000 the next time.
Yes, I mean, when you say it jumps back and forth, the SMT solver jumps between different models. That's correct. But our calculus is not affected by that because the model that the SMT solver finds for the resolvent is not part of the state. So in this step here, from this state to that state, the SMT solver can simply switch to a different model, but that doesn't affect our calculus at all. So we do not have to do additional steps with our calculus due to that.
Okay, thank you. And any other question, Andy?
Okay, so this acceleration technique seems to rely on the fact that instead of doing a single step, you can do like a symbolic number of steps. So you can introduce the n, which gives you the clause 4, and that's the thing which allows you to do these sort of quantum leaps. Okay, so you can sort of do that when your constraint system here is a system of inequalities, because you can introduce a fresh variable there. Mm-hmm. Okay, so that sort of begs the question of, if you're working over different constraint systems, how can you then symbolically capture the fact that you're doing lots of compositions of the constraints and represent the number of compositions symbolically with a number? Have you got any answers to that? I don't know if that's a silly question. I've got no idea.
So if I understand your question correctly, you're wondering what happens if so here we have equalities essentially, right? The new value of x is the old value of x plus 1. That's an equality. So you are wondering what happens if this is an inequality and x gets just set to a larger value, but we don't know how much it is increased specifically, right?
Oh, yeah, that's true. No, I wasn't even wondering that. I was wondering about what happens if you operate over a different constraint system. When you're outside the world of equalities and inequalities, because the systems, there are lots of different constraint systems which are interesting in sort of program analysis.
So you mean like different theories?
Yeah, like different theories.
Okay. So different theories are very interesting.
Okay.
So I think if we go to reals or rationals, that's going to work basically in the same way. We have some ideas for arrays. That's basically work in progress. I hope that we have something for that in the next year. Bitwork vectors should work without too much hassle. Floats are going to be a nightmare. So it really depends on your theory. So you can integrate any theory into this calculus where you have these acceleration techniques, but for every theory you have to develop these acceleration techniques from scratch, essentially.
Okay. That makes sense. Thank you.
Yeah, thank you very much. So I also have one question that is maybe slightly connected to Andy's question. When I look at the examples that you have shown, it kind of reminds me of what we would see if we analyze a program and try to have a relation between precondition and postcondition. So it's a kind of relational analysis. And if we do it with some abstract domain, abstract interpretation technique, and say we use polyhedra or different abstraction, the path from the problem to the solution would be slightly different. We would use widening, we would use abstract postcondition. So my question is, did you try to look at a correspondence between the resolution steps that you would do and the analysis steps that we would observe in such cases?
Not really. So the thing is that we were mainly interested in proving unsatisfiability, and most of the existing techniques, in particular abstract interpretation-based techniques, use over-approximation. So if you get to an error state, you still have to do some kind of post-verification that you actually have a real path to the error. And we wanted to avoid that, so we used these acceleration techniques, which are precise if they apply, so that we do not have to do this post-verification step. So that's, I think, a crucial difference between this approach and many others.
Fair enough. Any more questions? I see no online questions, so I think we are going to thank Florian again for the nice talk and the discussion.